Let me share my screen. Okay, it's shared. I just started the recording. Okay. So totally today we are basically planning to finish. Let me show you this thing. Just a second. This planner. So like today is ninth, right? So if you are able to complete up to 9 bias, then it would be good, because after that these topics will take like one day. Logistic regression, linear, this optimization problems, which contains all of those problems, are like this is nothing but the maths repetition, all those like derivation, first derivation, second derivation. So this will not take time. But then support vector machine, we have like so much of thing, dual form and primal form, and formulas based on that, and numericals, right? So tomorrow, if we are able to finish this, and on the last, on the 11th, I have kept like decision tree and ensemble models, just two topics, because if something is remaining from 9 and 10, we can catch up on 11. So by 11, if we are able to finish all these theories, definitely with like all the intuition behind, intuition and everything, all the formulas also, then we will have 2 days, like 2 full days, 12 and 13, to finish our mock 1, mock 2, and meet. Like for mock 1 and mock 2, I have made the notes, like last 10 questions are only remaining from mock 2. So I'm writing all those things, you can say, all the formulas, and I am solving it on the paper basically, with step by step, right? And I am also preparing this Excel also for the solution of the questions. If you're able to see my screen, right, from mock 1 and mock 2, how to solve it in Excel and like that, correct? So last 2 days we will dedicatedly have for this solution only, mock exam and mid exam. Correct. So let's try, like if we are able to finish to nine bias, otherwise we will take nine bias tomorrow. Okay. So the first one, or you can say the week one, we had all the NLP related topics, right? So by this time, we really understand like why we need this need natural language processing, and why we are doing this, because machine cannot understand basically the sentence or word. This t is nothing but some ASCII value for machine, right? And this t is also having different ASCII value. So machine doesn't understand the language. It doesn't understand like apple on a table, right? So and the like the machine cannot make sense of a sentence. That's why we need to convert it into number format, or you can say vector format, right? So that's this thing. And in language we have so much of nonsense, so you can say, but it makes sense only to us. Something like is or in, some preposition, or some kind of this grammatical thing that we can, and this how this word has no like meaning. It generally makes sense like in the sentence, but the core meaning of the sentence is nothing but in this kind of a word, language, numbers, machine, this kind of a word. So first we will remove all the stop words, right? So this is nothing but it comes into the text pre-processing. So the first part in NLP is text pre-processing. That means make the whole word, or all things, all the sentences, or you can say corpus, right? Some in have some meaningful thing, right? Just remove everything which is not useful. That's nothing but the stop word removal, right? So this kind of a thing, M is R, A, and it doesn't add like any meaning into the sentence. And so it's nothing but the stop word removal. The next is stemming and lemmatization. So what's the difference between stemming and lemmatization? So yeah, in language we can have like so much form of one word: go, going, on, man, mouse, and mice, like this. So what stemming is doing is, for stammer all, and this for all the stammers, these are like very much useful stammers, like mostly use this Noble, Potter, and Leicester. They define some rules, right? How, which kind of rule? Let's say if I have ing, just remove it. If I have ies, just remove it and put y, like those kind of a rule. So this stammer are nothing but it doesn't look for the complete meaning or the meaning of a word. It just cares about the rules, set of rules. Based on set of rules, it converts the word, right? Change the word meaning, change the word basically. And after stemming, it's possible that it doesn't make any sense, On other hand, in lemmatization, what we are doing is we are using, see, it is using this library called WordNet. So WordNet is like on Earth the highest, or you can say the biggest data set related to word. All that meaning, semantic meaning, and everything. So what lemmatization is doing, it will kind of see a word and try to convert into one useful, or you can say a very like meaningful word. So from CAD it will convert to CAD, right? Because like lemmatization method understand like this is in past, so it might have some meaning or something like that. So CAD to CAD. And snowball stammer, using some rule, it will just remove D. Water stammer will convert into CAD. But this is beautiful. See, if the word is university, right, due to some kind of you can say set of a rule, it is converting into universe, and this spelling is also not correct, right? I guess we have E at the last. Lemma would be just university, right? And it will go crazy for easily. See, it is converting easily into this EASILLI. So what is the meaning of this word, right? So stammer is useful when you don't want to preserve the meaning of a word, right? And lemmatization is very useful when you want to preserve some kind of a meaning out of the given word. And so these are some examples. Correct. Say spottingly is converted to this kind of spottingly. In Potter stammer, snowball stammer is saying this spot. Right. So there are, and stemming can be useful. Like if you're doing some spam detection or anything that you don't need to give feedback, or you don't need to interpret the model, then you can go with the stemming. But if the meaning is very useful, then choose the lemmatization instead of stemming. Right. Let me then go to just a second. Okay. Then what we have in text pre-processing, the next topic is nothing but the tokenization. So tokenization is nothing but given the sentence, just take like the words one by one, separate the words from the sentence is nothing but the tokenization. So tokenization can be done in two ways: sentence tokenization, also in word tokenization we have. So if you have paragraphs of paragraphs, then you can tokenize into sentence also. Right. So if you have something like this, I machine learning aspirant, how are you? Hope you are doing great. NLP is good. So sentence tokenizer, if you are using in the library NLTK. So before using this, you need to download this NLTK download PUNKT. Right. Or if you say word tokenization, then it will convert like each word: high, machine, then learning, then aspirant. And sentence tokenization, it is separating all the sentence out of this para. Right. So nothing fancy here. Things will go crazy one by one. Okay, next is nothing but binary bag of word or bag of word. First is bag of word, and another flavor is binary bag of word. So this can be asked in the exam, that given this kind of a sentence, this three sentence, convert the binary bag of word. Or they may ask like which two sentences are very much similar. We had this kind of question also, right? If you are using binary bag of word or simple bag of word, which two sentences are that they will say this sentence 0 and sentence 2 are very much similar, right, than any other sentence? Yes, because these two are common. Let's see how first bag of word works. So as the name suggests, bag of word, what we need to do is just create the bag of a word. So given this corpus, after like cleaning and removing, thus we have this three sentence: believe God believe, greatest sin think quick, believe world fit. So this is nothing but some Swami Vivekananda quotes. So what the first step is to nothing but create the bag of word. Actually, in my previous video, I had a problem. Like I was applying the bag of word very differently. I was saying believe equal to three, but that's not the correct way. Sometimes they are using it, but this is the more standard way of bag of word. So out of this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we get this unique words. Believe God. This 1, 2, 3, 4, 5, 6, 8 unique words we are getting, right? So in our bag of word we have 8 unique words, right? So every word can be represented as 1 1 1 1 1, right? This is not compulsory, but in my bag of word I have 8 words. So given any sentence, what I will do, I will take these 8 words, 1 2 3 4 5 6 7 8, and I will assign the number as the number of repetition in the sentence. So if I am converting, or let's say I am converting this sentence into machine learning language, that machine level language, there's nothing but in number or vector format. Then what I'll do, I will take believe, got believe. Okay, first word is believe. How many times believe is occurring? Two times. So two. Then fit is occurring? No, then zero. God is occurring? Yes, one. Then greatest? Zero. Seen? Zero. So whatever like words I have, I just write the count as easy as that. Greatest, seen, thick, weak. So greatest one, seen one, think one, weak one. Every other place 000. Right. So the what we have done is we have taken this three sentence and converted into the vector. Right. So what this vector are representing? Just nothing but the count of a word. And binary bag of word is like no brainer. What it is doing is just convert like everything into binary. So if word is there, if believe is there, like it doesn't matter how many times, one, two, three, just put one. If the word is not there in the sentence, just put zero. That's what binary is, right? Yes or no, one or zero. If the word is there, just one. If word is not there, zero. Right? So this is the simplest one, but it doesn't carry any kind of semantic meaning, or it doesn't give any damn shit about like very occurring word or very important word. So binary, this bag of word has nothing to do, like very not very useful, but this is the simplest method that we can think of, right? If we need to convert this sentence, English sentence into this thing. Now what you can say, this mathematical representation or vectors. Now this vector can be fed into machine learning model, right? Because we cannot give this sentence into machine learning model, right? So this is the simplest technique. Let's take the next thing, TF-IDF. Right. So this is the most important one, and very you can say simple thing, but very powerful as well. So what TF-IDF is doing, using TF and IDF, it is trying to preserve, like get the information at local level and global level as well. This was also one MCQ or MSQ, that TF IDF like in TF is is getting the local level information, and IDF is taking the you can say global level information. Let's see what does that mean. So TF is nothing but the term frequency, right? Term frequency, and TF is calculated document wise. So there is one some terminology. It should be somewhere there. So what the document is, what the sentence and what corpus is. So if you have like the whole paragraph or the total data that you have, it's called the corpus or corpora, right? And inside that corpus you have like a different sentence, right? Or if you take the different paragraph as let's say input, if you are taking paragraph as an input, it's called the document. If you're taking sentence as an input, it's called document, right? So inside this document we have these terms. This is the first. So these all are nothing but the terms. So what TF is saying, TF is nothing but the term frequency, and it's calculated document wise. Because using TF, term frequency, we are trying to find out the meaning at you can say local level. What I mean by local is at the document level. So document level, term frequency is defined as TF, or term frequency is, as you might have guessed, number of words in the sentence, or you can say how many times the word is there divided by total number of word in the sentence, right? So TF is saying like how many time or what's the frequency of a word, or how frequent this word in a given document, right? So it doesn't care about all different or you can say other sentences, right? So if you are finding term frequency of document, so what it would be, so it would be how many times I have document here. So I have like just one time, and how many words I have, one, two, three, four, five, six. So term frequency would be nothing but 1 by 6, as simple as that. But the term frequency of document in second sentence, if I talk about, then how many time I have document, 1 and 2. So 2 divided by how many this thing I have, how many you can say words I have or terms I have. So one, 2, 3, 4, 5, 6. So 2 by 6. Right. So it is different from first sentence. So term frequency makes sense on the local level, and IDF. Let's see what the IDF is. So IDF is calculated at the you can say global level. Global means corpus level, all the whole data. So what IDF is looking for? So it's nothing but inverse document frequency. Inverse document frequency. So it is the reverse of frequency. So what is the frequency? Frequency is nothing but a number of times something is happening divided by total. So it is inverse. So it's nothing but total number of sentence divided by number of sentence containing the word. So it is inverse. See, if it was frequency, then it would be nothing but number of sentence divided by total number of sentence. But it is inverse. That's why we are taking total in the numerator and number of sentence, or you can say occurrence, in the denominator. Right. So total number of sentence. How many sentence do I have? So it's one, two, three, four. So this is always a constant. So this is always constant. Four. Divided by, what's the meaning of this? Number of sentence containing word. So let's say I want to calculate the IDF of let's say word document. So how many time document is occurring? One, two, three, four. So do I need to write four here? No. What it is saying is number of sentences containing the word. So document is there in first sentence? Yes. Document is there in second sentence? Yes. How many times? We doesn't care. We don't care. Right. So number of sentence we need to count. In third sentence, do we have sent document? No. Third, yes. So we have document in three sentence out of four. So four divided by three. ln of four divided by three. So this is nothing but the natural logarithm. Natural logarithm, right? Natural log. And why we are taking log is because and see, the log has like one good, you can say, property, that if you take the inverse document frequency of this, so it is occurring in all the documents. One, two, three, four. And how many sentence I have? Seven. Four divided by four. So it would be nothing but one. And ln of one is equal to zero. Right. So natural log. And there is one more. There is one more. You can say reason to use ln is that the in English word all these words as thus follow the power law distribution, and it is not continuous, it's discrete basically, because it cannot be continuous because we have like different words, right? It is not real value number, but it follows this kind of you can say power law distribution. That's why we are using this ln. And in msq they like use like you can say they said like this idf is used to decrease, you can say decrease or you can say, oh, if we don't use ln, then what will happen? Let me first tell you that. So if you don't use ln, then what will happen? Let's say number of sentence are 1,000, right? And in just one sentence there was one word something, let's say uh, fabulous word was just in one sentence. So what is the idf value? 1,000. And term frequency of, let's say, fabulous is nothing but zero point 0.3. So this is overpowering the tf, right? So this is like a high, you can say, value, high impact, right, on total TF IDF value. TF IDF is nothing but TF multiplied by IDF. So if you don't take ln, or you can say natural log, or any kind of a log, here they are taking natural log, then this IDF value will impact much compared to TF value. That's one more reason to use natural log. The other reason is nothing but these words have the power law distribution, right? So some very common English sentence word like words, this, is, the, a, and those kind of word like occur very much almost in all sentences, right? That's why we are using this natural log, right? So that then it will follow like some uniform, or you can say we are basically what you do. If you take the log of 1,000, then it would be nothing but only 3. So we are kind of suppressing the thing, right? Suppressing the overpower number, or very much high value, right, compared to tf, term frequency. So these are like couple of reasons that why we are using natural log, because like uh, this kind of thing, like they can convert into mcq and msq, right? So that's how this idf value is calculated. Now I guess it's trivial. So here we have taken this kind of this kind of this one example. So if the word is occurring like in each document, the idf is literally 0. 4 by 4 is 1, correct? So ln of 1 is nothing but 0. So tf idf would be 0, right? How many term frequency this word has or is word has, the total tf idf would be 0. If and see, if you think intuitively, in this word, in this sentence, there is no like what this is doing, right? What is the use of this word and this word? Nothing, right? Because if you in the first sentence, the most useful information is somewhere here first, and you can say document at some extent, right? But document is occurring also in like almost every sentence. So the most useful word is nothing but first. Here it is nothing but second, and here it is nothing but third, like this. Correct. And the last sentence just we are asking is this document. So if you think if the word is occurring like almost in each sentence, then definitely it is either a preposition or article or something like that. Correct. So definitely see, if you see, the IDF value is very low for this is the see, because it's in document also, because it's occurring like in all the documents, right? So how to calculate this? First calculate all the term frequency for given this thing, given all the terms, or you can say words. IDF can be calculated beforehand because IDF like is independent of all the documents, because it's calculated as this thing, global level or corpus level. Correct. So first calculate all the idea for unique words, then calculate the term frequency. So if you want to calculate term frequency of this, so this is occurring like just one time divided by total number of words, 6. 1 by 6 is nothing but 0.1667. Then multiply TF and IDF. So you'll get the TF IDF value. So these all are the TF IDF value. Correct. So that's how we convert our sentences into vector form. Right. So that's how like TF IDF is calculated. Any doubt, guys? And this would be cakewalk until we hit that LSH KD tree and maybe nav bias. Okay, n-gram boring. So n-gram is nothing but how you can say tokenize the sentence, or how you tokenize the sentence into word. So and how much like how big group of word you are taking, right? So if you are taking unigram, that means nothing but divide, like take all the words. Let's see, has not passed. Bigram, just group of two. And don't skip. See, while taking group of two, don't do something like this. C has, then not passed, then the big no. C has, then has not, then not passed, then passed the, like that. Correct? And while calculating unigram and bigram, if they ask something like this, and you'd be surprised. We had this question also. They ask like the number of unigram plus number of bigram, right? They said like if n-gram equal to 1 2, then how many you can say unique words you will have if you are using unigram and bigram, right? N-gram 1 2, that's nothing but unigram and bigram. So definitely we need to calculate this thing, how much unigram we have, how much bigram we have. And while calculating this, just keep in mind we should not repeat the things, right? If note is there and again not is there, it doesn't count two, it count one, it counts one, right? So while calculating unigram or bigram, after having this, just remove the duplicate, right? Just keep one of them. Yes.
Mayur, what you said, what to remove here?
The here like I guess nothing is repeating, but if let's say something is repeating, right, then it doesn't count like twice.
So in a sentence anywhere, or
No, no,
I mean
while
that would,
calculating unigram. So unigram is nothing but the unique words, like unique single
yeah,
words
yeah,
in the sentence.
correct.
So if you have something like this, this is the, and let's say for some reason again I have this is it. So if you calculate the unigram, then it would be 1, 2, 3, and 4 only, because this is repeating, right? This and is. So if even if you are calculating bigram, then how many bigram you will have? Just 1, 2, 3. This doesn't count. This is like this, and is like is repeating is it. So the this is then 1 2 3 4, only 4 bigrams, right? And 1 2 3 4 unigrams, like that. So don't
Yeah. So
repeat. Yes, in unigram and bigram, nothing like it. It should not repeat.
yeah, basically first you have to create vocabulary and do all this stuff.
Hmm. Correct. So
Yeah.
unigram and
So
bigram is nothing but the tokenization. So we are just having the vocabulary like for TF-IDA, for bag of word, or let's say even if you are that word to wake, I guess we can give the direct sentence, but any algorithm. So this is nothing but the vocabulary, right? It's kind of a dictionary. So it should not have the repetition. Correct. Yes, it should be sequential. Yes, we cannot take something like this C and past the in examination. Correct. Thanks for
so
pointing out, Vikas.
so in last example that you were writing with a red pen, I think there should be only three bigrams. This one. This is the it, right?
So
This is the
bigram,
it.
how many bigram you are saying?
Three.
Uh, just a second. Arey yaar, why it's going? Okay. So this is the and this and is it. So four, no? And we need to go in sequence. This and is and then the and this. So these and is I won't take because it is already there, right? And last is and it, correct? So
So
there would be four.
bigram duplicates you will remove. Okay, okay.
Hmm. In
Mhm.
unigram,
Bigram
bigram, or
duplicates.
trigram, we can't have the
Uh-huh.
duplicate.
Correct, correct, correct. Yeah.
Correct?
There's one good example in the comments you can see actually under this video.
C has and has C are treated as repeating. No, no, no. C has is different than has C. The sequence matter. Okay. Let's see like word to whack. So word to whack is nothing but it's using some neural network model and try to understand the semantic meaning basically, right? So what word to whack is doing? See, given the semantic meaning, so what I mean by semantic meaning, see there is some you can say meaning between man and king and woman and queen, right? Because king, like it's nothing but king and man, like the same relationship between king and man is in terms of like semantic, or you can say in the language, it's nothing, it is like same relationship, it's between queen and woman, right? So these two vector won't be same. It would be like in the same direction it would be pointing. So there would be very much like very similarity between these two things. And I guess they are using cosine similarity. So these two are like having the same angle, no? So cosine similarity would be highest one. Angle between these two is zero, right? Because they are both are pointing in the same direction. So in word to vec, like all this semantic meaning are preserved by having the, you can say in the same direction you'll have the vector. So two vector like representing the same semantic meaning would be similar, not the same. Right? So these two vector are not the same vector, right? And it tries to like preserve like as much as meaning, or you can say semantic meaning of the words, right? So say slower and slowest are like are connected to each other with some meaning we know. So faster and fastest would have the like similar you can say direction arrow, or you can say vector representation, right? This kind of thing. So this will happen in word to vec. So what word to vec is doing, it is using some kind of a neural network model inside, and it will learn all the like if you gave the like whole corpus, right? Google has given like whole, you can say, news data, and it will learn all these kind of beautiful things, right? Even Paris, France, this capital information is also preserved. Say one more example. So this is all about the word to vec. In 2017 it was you can say de facto, or what I say, that state of the art technique at that time 2017. In videos are also mentioned. Today it's I guess BERT or some kind of a transformers. Sentence vectorization. So till now we have seen like how to convert our word into vectors or even the sentence also. But using word to vec, how, see, word to vec is useful. Like you will get the vector for man, vector for cat, vector for dog, like that. But how can you convert the sentence now? So given like all the vector, like he is from the England, so he, for he, you know, is for no, from in England, you know, like what is the vector. But how you convert the sentence, whole sentence into vector? So there are two simple techniques. The first is nothing but take the average, and nothing fancy, the simplest one, right? So what you will do, you will take all the vectors, given all the vectors, 0 1 1 1 1 2 1 3 3, just to take the summation and divide by the total number of words you have, right? Sum divided by n. So simple average, we are just taking the average of all the word, all the vectors. But this is like not good, or you can say not very indigenous, or very, you can say, interesting way, right? And very dumb way, just taking average. So what we will do, we know like what tf-idf is, right? So tf-idf like holds some kind of semantic meaning, or you can say some weight over all the word, like how that word is useful in all corpus or in the sentence basically. So what we will do, we will calculate first tf-idf for each word. Then let's say ti is nothing but the tf-idf word I. So for all the word 1, word 2, word 3, word 4, we will calculate t1, t2, t3, t4. So it's nothing but the tf-idf value, right? How much that word is important. Then what we will do, we will take the weighted average. So what weighted average is nothing but, just take like just multiply this tf-idf value, what you will have, multiplied by the first word. tf-idf value of the second word, it's nothing but t2 multiplied by second word vector, up to the nth tf-idf of the nth word and vector of nth word, right? So this way we are converting our the sentence like comprising of n words, different words, w1, w2, w3 to wn, using word to vec and tf-idf. So it's nothing but tf-idf weighted word to vec, right?
So will there be any numericals on computing this word to vec as well? Word to vec.
No, word to weight we cannot calculate, right? Because it's kind of you can say framework that you give the corpus, and using some neural network magic, it try to find out this. But definitely they can create a very small or small example on it, right? Given the vectors 0 1 2 1 1 3 4 6 7, calculate the average word to vec, or what would be the vector representing this sentence, right? So it is possible, just you need to take the summation of all the vector divided by n. So it is possible. Or we have this medium or hard level question. So in that case they can give you like three sentence, simple small three sentence, and word to vec, the vector representation of the word, because that we cannot calculate, right? And they can ask like tf-idf word to vec. So first we need to calculate tf-idf for each word. Once we know the tf-idf value, then we can calculate this, right? So in two steps we need to calculate. So this can be made, right? So this is possible. They can, if they have time, or if they find something. So possibly they can ask. But we know
Or
like
they
how
will
to
can
calculate
just
TF-IDF.
ask
Uh-huh.
formula itself. They can just ask the formula itself.
It's also
TF
possible in
idea,
easy.
TF, yeah, T1 into what? I mean W1 vec and stuff. Or they will divide it by n, like you have mentioned the
Hmm.
notice at the bottom. So just to confuse,
Mm-hmm.
like you mentioned at the bottom, notice that we are not doing dividing for the
Correct, correct. We are
TF
not
idea.
taking average. Yes, correct. So it's also possible that they can confuse with it, right? One by n, then T1 W1, T2 W2, like that. Yes, correct. So guys, beware. Okay. So any doubt in this topic? Yes, we are going at a good pace. It's just 10 10. Sorry, this index. Just go like once. So we just saw the text pre-processing, the stopword removal, stemming, lemmatization, tokenization. Then bag of word, one flavor of binary bag of word. Flavor of bag of word is nothing but binary bag of word. Then what's the TF-IDF is? Term frequency, inverse document frequency. So IDF is inverse, total divided by number of sentence, right? And ngram, uni, by, try, chord, word to vec, right? And using the word to vec, how to you can say tokenize or convert, vectorize sentence, right? Simple strategy is taking average, and intelligent technique is nothing but using the TF-IDF. Right. With this, we just finished the first part. Let's go to the machine learning. So, like we have like three left. So, machine learning notes. Now it would be easy. Like 4 or 5 topics will mostly take time. And compared to like subject one and subject two, this is also fresh, right? Because just 2 weeks back we had the exam. So okay, so this is I guess week two, the simple intro to machine learning. So the basic like, whole idea about machine learning is nothing but in traditional programming, we'll write the logic basically. Given the input and the program, given the input, we write the program, right? We write some kind of a function. Like what is the logic behind this, right? Even I have seen like in my project for forecasting, they are using formula still now in inventory. They use formula for even upcoming 10 years also. Their formulas given the past data multiplied by this factor divided by this factor and this and you'll get the forecast. Still they are using it, right? So in traditional programming, we write the statistical formula, well proven formula theory, and we give the output. But in machine learning, when the data is very much high, not interpretable, how you interpret the audio? How can you write the traditional code to interpret the audio? How can you convert into English language? How can you translate it? So machine learning is nothing but you give the input and you also give the output. In case of unsupervised learning, you don't give the output, right? So this output is optional basically. I must have here I have given it, right? So in supervised learning, you give input and output. Machine learning model will try to find out the pattern out of it, right? In whole crux, machine learning is nothing but the finding out the pattern, and it will give you the program basically. This is the logic, right? These are the weights that if you multiply with the input, you will get the output like that. Right, so after like it give the program, then we apply give the input. So it's nothing but the taste input, or you can say the real world input, and it will now generate the output. So this is the main difference between traditional programming and the machine learning. Okay, now let's start our the first, or you can say the simplest method. And first we will start with the classification, and then we'll jump on to regression. So in classification, what we are the first or the simplest method is nothing but the k nearest neighbor. So the idea behind KNN is nothing but given the data point. If I say like if you don't know anything, any machine learning, and if I say what is the classification of this data point, then definitely you'll say it looks like blue. How? Because like in neighborhood you will have all the blue data point. So the chances of this query point of being blue is very much high. So this is blue. You will classify it. So what KNN is doing the same. Given the query point, find out the nearest neighbor, k nearest neighbor, 1, 2, 3, 4, 5, 6, k can be anything, and take the majority vote. If the majority is of class A, then say it's class A. If majority is class B, say class B. So that's the whole crux behind the KNN. And how to choose the value of k, let's see. Okay, first thing. So how will you say like this is the neighbor or something like that? How are you defining that? So what you are doing is like how many points are very much near to this point, right? So and if you want to calculate like how many points are very near to this query point, you need to calculate the distance, right? On like which parameter you are using to descend on this neighbors. How you are saying like this is neighbor is nothing but which is at very small distance, right? So it's neighbor. So how can you calculate the distance? So in like real world, it's very simple. But in machine learning, we have so much of distance matrix. This is just three. There are so many, or you can say like 8 to 10. Like I saw on Google, like in one cheat set. Yeah, so we will understand these three basically or four distance measures. How to calculate the distance between 2 points, because it will be useful like in K and in logistic regression, support vector machine, mostly everywhere, right? So the first and the very easy method, or that we know like in geometry, is nothing but the actual distance basically. What's the actual distance between these 2 points? How will you calculate? Right, so it's nothing but using the Pythagoras or anything. It's nothing but the Euclidean distance. The actual distance between 2 points. It's nothing but Euclidean distance. And how it is defined is under root for all the points bi minus ai square. Right, so b1 minus a1, b2 minus a2. You can even take a1 minus b1, a2 minus b2 because we are taking square, right? So this order doesn't matter, right? A1 minus b1 or a2 minus b2 you can take. And if I'm asking the Euclidean distance for, and this is also sometimes also called norm also, and if you're talking about just 1 point, right? So see, if a is nothing but something like this, a1, a2, a3, and how will you write the first norm, or sorry, second norm of a? Sometimes it's written like this, or double line is also nothing but norm 2. So it's nothing but under root b is not there, right? So a1 square ai square. So ai square is nothing but a1 square, a2 square, a3 square, like this. A1 square, a2 square, dash dash dash. So this is nothing but the second norm, right? So this is also Euclidean distance. Just to give you the context, Manhattan distance is nothing but mode of bi minus ai. Mode of bi minus ai. So total difference between in the first dimension, second dimension, third dimension. In all dimension we are taking the step of the difference, right? So if let's say a equal to 0 0 0 0 and bi is b1 b2 b3 up to bn, let's say 1 2 and 3. Let's take one example because this is very useful. 1 2 and 3, this is one point, right? Let's say point b, and I want to calculate the Manhattan distance from the origin is 0 0 0. So 1 minus 0, 2 minus 0, 3 minus 0, and I need to take the sum. So 1 plus 2 plus 3 is nothing but 6. So how the Manhattan distance is 6? So if I take three-dimensional geometry, something like this, right? So let's say this is x-axis, this is y-axis, and this is z-axis. Let's say, right? So so from origin, if I need to go up to b point, then what I need to do? First bi minus ai. So 1 minus 0 1. So 1 1. So this is nothing but in x direction. The point is at 1 minus 0, 1 unit far away from origin in x direction. So I will go 1 unit there. Then 2 unit in y direction, 2 minus 0, right? So 2 unit in y direction, so 2 unit in y direction, 1 and 2. So now I am here. Then 3 unit in z direction, so 3 unit in z direction. Now I am at b, right? So this is nothing but the Manhattan distance. 1 plus 2 plus 3, 1 plus 2 plus 3 is nothing but 6. And Euclidean would be something like this, direct. Alright, let me use another color. Direct distance. Under root 1 square plus 2 square plus 3 square. So it's nothing but the Euclidean distance. Correct? That's how like this Manhattan distance makes sense. Like we are just calculating the difference between all the dimensions. Bi minus ai, take the absolute value and go reach the point basically. Right? Minkowski distance is nothing but the generalized form, you can say, of all this distance, Euclidean Manhattan, or any generalized form. So what I'm doing is I'm taking the pth root. So 1 by p raised to 1 by p is nothing but the pth root. Second root is square root. Third root is nothing but cube root, like that. Taking the sigma, I goes from 1 to n all the points. Bi minus ai, absolute value I'm taking, bi minus ai raised to p. So if I take p equal to 1, so this will cancel out. Right? First root is nothing but as it is, and this will cancel out, raised to 1. So it's nothing but Manhattan distance. The formula would be exactly as Manhattan. If I take p equal to 2, the formula would be exactly its Euclidean distance. And so Minkowski distance is nothing but the generalized form of distance measure. Put p equal to 1, you will get Manhattan. P equal to 2, get Euclidean. P equal to 100, and things will go crazy. You can take even p equal to 0.25 also. Okay. Hamming distance. So surprisingly, like we had two or three, maybe two or more questions from Hamming distance, and every day every question was based on like more than two. Basically, three questions I can remember now. So three questions were definitely from Hamming distance, right? So the easiest topic, but more questions like most favorite of paper setter. So what Hamming distance is? The simplest distance you can say. So Hamming distance is nothing but like take all the dimensions, and how many dimensions like these 2 points are different. So it's nothing but the Hamming distance. As easy as that. So just say it is different at here. Yes, one, two, three, four. Literally, we need to count all the places when it is different. So one matches, zero zero matches. So it doesn't count. Zero one zero one one zero zero one like this. So we need to find out like at how many places it is different, and it would be nothing but the Hamming distance. So 1, 2, 3, 4, 5, 6, 7, 8. So Hamming distance between A and B is nothing but the difference of all the points between all the points in each dimension. X
It's
dimension,
kind of
Y dimension, Z.
A XOR B, right? A XOR B. Having
Yes.
distance.
X or B, yes.
A
Definitely.
XOR operation.
XOR operation, no. When it would be one, when it is different, then it would be zero, no. So it's opposite of XOR,
So, okay, yeah.
correct. So if it is different, then XOR is zero basically. XOR is zero if it is different. So it's opposite of XOR, like that. Okay. Negation of XOR, yes, rightly said. And they what how they are asking is they are saying absolute of a minus b greater than 0 like that. So in numpy if you take absolute of a minus b, so a minus b either it would be minus 1 or plus 1, so absolute would be 1 1 1 1, and greater than 0, so it will count everything. So they are like asking like this length of absolute of a minus b. So like I don't know, like they've gone crazy, like they found out so many ways to find Hamming distance. Okay, just one use of Hamming distance I have noted that in genomic study to compare the DNA sequence. If like you have very large, you can say like millions or in thousands, you can say if the length of this string a and b are very much like in thousands of million or millions, then definitely Hamming distance will be helpful. And you just want to see like how much difference I have, then you can use the Hamming distance, correct. Next very useful topic, cosine similarity. And so just we saw like this distance are measured like in this format, or you can say linearly, right? In some units. But what about this thing, cosine and sine and everything? Because the each distance can be represented in this linear format or angular format also. So cosine similarity is nothing but the angle, cosine angle between two vectors, and this will make sense in higher dimension also because it's very really easy to calculate cosine similarity. And as the dimensionality increases, the Euclidean distance, or you can say the distance between 2 point, it has no, you can say, value, or it doesn't holds true basically, right? Because it's it's fact that if you go like in very high dimension 4 5 6 or even higher, every point is like at same distance. And I don't know how to represent that, but I just read somewhere. So cosine similarity is nothing but simple cos theta, and cosine distance is nothing but 1 minus cos theta, right? It's easy to get confused, but cosine similarity is nothing but cos theta simply, and cosine distance 1 minus cos theta, correct. So and if you are ever confused, just think about the case that what happened if theta equal to 0, that a and b are very similar, right? Because they are on each other, the theta is nothing but 0, very similar. So what you do if you do cos 0, cos theta cos 0 would be 1, and 1 minus cos theta would be 0. Now you tell me this is 1 and this is 0. So this should be similarity or distance? It should be similarity, right? Because it is higher and these two are very similar. So cos theta is nothing but similarity, and 1 minus cos theta is distance. Just take opposite example, pi by 2, or you can say 90 degree. right? So these are very different. So if you take cos 90, so similarity is 0 and cos distance 1 minus 0 is 1. So the distance is large, yes, 1. Similarity is less, 0, yes, correct. And what is the range of cos theta? 1 to minus 1. So maximum similarity you can have is 1 and the minimum similarity you can have is minus 1. Maximum distance you will have is 2. 1 minus minus 1 is 2 and the minimum distance is nothing but 0. Alright, so cos similarity goes from minus 1 to 1. Cos distance go from sorry minus 1 to 1, go from 0 to 2. Right? So this is nothing but cos similarity and cosine distance. And cos theta, as we know, is defined as a dot b divided by mod a mod b. So if a and b are unit vector, then you can remove the denominator. Then it will be simple as a dot b, right? A dot b. So cosine similarity. Okay. This we saw like in first subject also. Okay, just the dot product. Okay, this is very useful. Relationship between Euclidean distance and cosine distance. So, Euclidean distance square is nothing but 2 into cosine distance. Or you can write cosine distance is nothing but 1 minus cos theta. So, 2 into 1 minus cos theta. There was one example on it, and definitely it would be there. Like, there are high chances to be there in the final exam also. Given the Euclidean distance, find out the cosine similarity or the angle between two vector also. The question was angle between two vector, right? I remember all this because I was just making notes today morning. So this would be useful to like connect mid same paper and how they are asking, right? So this is the simple formula: Euclidean distance square 2 into cos distance or 2 into 1 minus cos theta, because cosine distance is 1 minus cosine similarity or cos theta. Okay. Just a second, let me have some water. Okay. So let's see like what how the value of k plays a role. I guess this would be very now you should be remembering this. So if you take k equal to 1, it would be kind of a overfitting, right? What I mean by overfitting is it is trying to like make sense out of all the points, right? Here it is saying it's red area, here it is saying it's red area, here it is saying blue area, but we know the boundary should be something like this, right? The boundary would be something like this. These are outlier 1 2 3 and 3 6 are outlier. But if you take k equal to 1, it will try to overfit, right? If you take k equal to 2, it's not able to find out the exact 2, you can say, or there is a tie between something like this. That's why we have this kind of a white area here and here, right? As the value of k increases, this boundary would be really really good, you can say very very definitive like this, correct? Now it is separating these two very easily, and it doesn't mean like take the value of k equal to 100. Th- then it will underfit, right? We will have like very good diagram, I guess. This diagram, overfitting and underfitting. So, what is the problem with overfitting, right? You will have this question like, if we take k equal to 1, the accuracy would be 100%, right? Because every point is classified very cool, very, you can say, rightly. Blue is classified blue, red is classified red. But the problem with overfitting is, let's say I have the query point. This pink is the query point, right? So, what would be the classification of the query point then? The classification would be nothing but blue, right? Because it is in the area blue. But if you think intuitively, the you can say true boundary is something like this, right? And this should be classified as red. But due to overfitting, I am making some mistake. Also, this point should be classified as blue, right? Because in the it is in the right hand side, correct? But due to this overfitting, I am saying it's red because it's the nearest neighbor is red, right? K equal to 1. So these mistakes you will make in the testing phase. Right, so that's the problem of overfitting, and this is called the high variance. See, it is varying much. See, da, like this squiggly line, as the state quest Josh said, squiggly line, right? So you are not getting the straight line or something. So what is underfitting then? Let's that I said, like if you say, like if I increase the k, this overfitting would be good. So let's take k equal to 1,000, 1,000, 1,000,000. What the problem? The problem is if you take like higher value of k, let's say I have 7 points and I take k equal to 7. Then what will happen? Each point in this area would be classified as the majority point because red is in majority 1, 2, 3, 4. Blue is in minority 1, 2, 3. So the majority is won by red. Right, so the whole area, if I'm taking k equal to 7, the whole area would be nothing but red area. Or you can say every point, this point, this point, and this point would be classified as red. See, this point is very near to blue, but due to majority, it is classified as red. Right, so if you take k equal to number of data point, then the majority, like whatever the label is in majority, will win. Right, so all the point will be classified as the label which is in majority right now. So if you take k equal to number of data point, then this will happen. So the best fit we need to find out, right? So if you go very low, it is overfitting. If you go very high, it's underfitting. A sweet spot you need to find out. So if you take k equal to 5, this outlier as handle, right? We have some outlier. You will in testing phase, you will make some mistake here. You will make some mistake here, but that's fine. If you are getting train accuracy, let's say 95%, test accuracy or validation accuracy 93, 92, somewhere around that, then you can say like this model can be generalized well, right? But let's say in training you are getting 100% accuracy, in validation you are getting just 70% or 80%, there is a problem. Definitely there is a problem, right? So that's all idea about overfitting and underfitting. Now let's see like what's training, validating, and testing phases. So in machine learning, what we do is first we take 60 or 70%. This like this depends on the problem to problem. So we will take like some chunk of a data. Like let's say we have 1,000 rows. So what we will do first, we will take 1,000. You can say data point. So first we will take just 600 data point and try to train the model, right? And we'll tune the model and try to get the best performance out of it, or the base model you can train on the training data set. Then what you will do, you will validate your model on the validation data. So till now your model doesn't know about this validation data set, right? So what you will do, if the model is not performing well, you will try to tune the model again, the find out the hyperparameter. Basically hyperparameter tuning is done on validation data set. Right? What should be the value of lambda? What should be the value of k or zeta or any hyperparameter you have, C in SVM, like that. Now, after, and if still there is a problem, then you will again go to train data. After doing hyperparameter tuning, again you will get to train data. Again you will see what is the accuracy I'm getting out of training data set. Again you will try to make some change, some you can say data engineering, sorry, feature engineering, and all of that stuff. Again you will validate it. After doing this exercise, that you are confident, then and only you will go to test data set. You will touch the test data set for the first time. And whatever the result you get, that's the final result. Now you cannot edit it, right? You can again go to train, validate, and all of this stuff from the scratch. But whatever the result you get in test data set, it's the final, you can say, performance, you can say measure of your model. Right, but the problem here is, let's say this 20% is gone. Okay, right? It is used for test data set. Now I have 80% of data to play with, but I am taking 20 as validation only. So and only 60% data I am using to train the model. So there is some problem, right? How it would be if I use all the 80% of data for the train and validate both, right? So 80% for the train. So that's nothing but the k-fold cross validation. So what we are doing is, we will separately, we have this 20% of data take aside, right, for the testing purpose. For 80% data, what we will do, We will divide it into k parts. So if I take k equal to 4, this is different than k in na? K fold cross validation, two fold, three fold, four fold, like that. So let's say if k equal to 4, let's assume k equal to 4, four fold cross validation, then how it will look like. So I will take 80% of data, divide into four parts, d1, d2, d3, d4. Then what I'll do, I will take the first part as the cross validation, or you can say validation data set for the cross validate, and train the model on D2, D3, and D4. Whatever the accuracy or whatever the parameter you get for the value of, let's say, lambda, you just note down lambda 1, whatever I get. Again, I will train on D1, D3, and D4, right? And cross validate on D2, whatever the lambda you get, lambda 2, let's say. Again, D3 as cross validation and D4 for cross validation. So in my training, I am using D1 also, D2 also, D3 also, and D4. Every data set I'm using, right? Every part of the data I'm using. So that's cool, correct? And after taking all the lambda, you can take average, weighted average, any kind of you can say strategy you can follow, depend on the problem in hand. You can simply take the average also, correct? So this is the idea behind k-fold cross validation. Um, okay, overfitting and underfitting we just saw. Yes, let me now make clear that what happened in the overfitting and underfitting, that bias and variance. So if I take the case of, so is this blue are nothing but the data point. Let me zoom it a bit. Right, so this blue are nothing but the data point, if you can see, right? And I need to fit a model, let's say machine learning model. So the first model, very of high variance, overfitting model is this black model. See, it is trying to get all the data point. See, all the data points. So it's kind of having the high variance. It is varying a much. If you change just simple 1.2 here, it will change, right? It will have like very high change, right? And it's trying to, it's not handling this outlier point. So this is nothing but the high variance and overfitting, right? So in overfitting, the high variance would be a very high, and the bias, no, it's exactly opposite. If you have very very high variance, then the bias is low. If you take the underfitting, if underfitting is nothing but this red line, very simplest model, very high bias, right? This using this point, and it doesn't care about this thing, this curve, right? So this is nothing but the high bias model, or you can say underfitting model. So variance is very low. It doesn't vary much, right? It is very straight. So the intermediate model with the, you can say, very like small bias or small variance is nothing but this green model. See, so as I increase the model complexity, so this variance and bias is nothing but about the like how complex model you want to choose. So if you choose very simple model, let's say I just want to have one polynomial of degree 1, right? That's nothing but the single line, simple line. This nothing but this red line, right? Your model would be very simple. It would be very fast because it's just doing some you can say multiplication and summation, nothing fancy. But you will, this nothing but the very simple model, or complexity is very low, model complexity, but it is underfitting or high bias. It is having high bias, or it is underfitting the model. Variance is low. In case of overfitting, see, now I increase my model complexity by 1. Let's say now I allow the polynomial degree of 2. So nothing but x square I am allowing, basically ax square. So if you draw the x square or minus x square, it looks something like this parabola, right? What is polynomial degree of polynomial 2? Sorry, degree of 2, polynomial of degree 2. So it's parabola, right? Anywhere. So now I just increase my model complexity by 1. So see, I got this green line. Now bias is somewhat reduced and variance is somewhat increased. Now if I allow the degree equal to 3, polynomial of degree to ax cube plus bx square plus 3, something like that. So I get this blue line. See, This blue line is very very good, right? Because it is representing this data. See, very good. Correct. But let's say I now I allow like highest complexity of a model, right? Go crazy, like classify all the point, or regression, like do the regression of all the point. Then I got this overfitted model. Overfitted model, that means high variance, low bias. Correct. So and the model complexity is very high. We will have one graph also, I guess, in the next PDF, that bias variance trade off. Okay. One more idea in weighted KNN. So, see why we need weighted KNN. Let's see. So, given this kind of a scenario, let's say we have this four blue point here, three yellow point here, orange point here, and I have this query point. So, what should be the category? It should be orange, right? Because it is very near to orange point. But if I take k equal to 7, these 7 are the neighbors of this point, and the majority is nothing but category B. So they will say this is blue point or violet point, blue or violet, you can say that. Blue point, right? So that's the problem. Then what this weighted KNN is saying, just take the weight as 1 upon distance, right? Or one, see, this can be done in two ways, and there was like first or second question also. Calculate all the distance of the query point for from all the neighbors. Wherever you take the minimum distance of, let's say for category A, the distance is nothing but zero point 0.3 plus zero point 0.5 plus zero point 0.4, right? 1.2 only. So if you have the minimum distance, then classify the label. Or you can take the weight. So 1 upon d, as the distance is down, as the distance is low, weight would be high, 1 by d, right? 1 by d, just the reciprocal. So if you take the weight, summation of weight is nothing but 7.83 for class A. For class B, the distance is higher. That's why 1 upon d, if distance is higher, weight would be lower. 0.9, 0.7, 0.8, 0.6, 3.15. So we will classify this point as category A. If you follow these two strategy, right? Minimum sum of distance, or maximum sum of weights, and weight is defined as 1 divided by d, or you can take 1 minus d also, right? But 1 by d makes sense, more sense, right? Any questions, right, guys, for the weighted KNN? They can like ask MCQ, MSQ, or see even some also, right? Is this variance same as sigma square in our probability? No, this is nothing but the variance of your model. Yes, it is somewhere you can say related, or like how much variance you have in your data. That's why they use variance term there. But in machine learning, like how much variance you have in your model, we are talking about that variance. There was a question, guy. I just I hope like you saw that. Is this variance same as sigma square in your probability? No. Uh, okay, so this is one more strategy in weighted in KNN. Very simple strategy, but very useful, right? In this kind of a scenario, weighted KNN. So weight is nothing but 1 by d, smallest distance, sum of distance, or highest sum of weight, right? That's why, like I say, like just have the core understanding, like how weighted KNN work, right? Because the question can be anything, correct? MCQ, MSQ, or anything. So if you have the core understanding, then and only you will be able to answer that. Uh, KNN for regression, just like three or four lines were there. So how KNN for regression works is, let's say this is the query point, or let's take the fresh example. Let's say this is the query point, that what is the income of this person given the age, last record, medical record, or last purchase record, or the credit card limit. Given all the parameter, I want to predict like what is the this thing, what is the income of this person. So then what I'll do, I will take let's say k equal to 4, or sorry, k equal to 5. 1, 2, 3, 4, and 5. So let's say these 5 are the nearest neighbor from the training data set, right? I calculated the cosine similarity or Euclidean distance by KD tree or LSH. I found out these 5 are the nearest neighbor. Then what I will do, I will take the income of 1, 2, 3, 4, and 5 and take the mean of it. Or you can take the median also. Right? Mean or median. It depends on you. Correct? So I will take the average of all these 5% and I will say this is the average of this data point. So this is nothing but what we are doing. We are doing regression. What's the difference between classification and regression? If you are calculating the label, class label of your data point, right? It's nothing but classification. Regression is nothing but if you want to calculate some real value, or you can say value of your output or dependent variable, right? Income, what would be the age, what is the age of the person if you want to calculate, or how many hours he or she will spend on my website, any kind of entity that belongs to R, or the real value basically. So it's nothing but the regression. Second last topic, KD tree. Third last basically. So in KD tree, what we have? So why KD trees were useful? So let's say we have so much of data point, 1 million data point. So will you go like calculate all the distance of 1 million data point? No. What you want to do is you just need to divide your area into some parts. So that's what KD tree is doing. So let's take this example and try to generate this KD tree. So how we can generate this KD tree? Right. So let me open this one. Okay. So, given this data point, how can we generate the KD tree? Let's see. So, we have just two dimension. In KD tree, what happens is we have the levels. This level 1, then level 2, then level 3, then level 4, then level 5. At each level, we compare only one dimension. And it goes from dimension 1, 2, 3, 4 up to n. Then again 1, 2, 3, 4, and 1, 2, 3, 4, and like this. Right? So, uh, here we have just two dimension, dimension 1 and dimension 2, or you can say x and y. So what we will do, at first level we will compare only x, second level we will compare y, then again x, then y, then again x, then y. If we had three dimension, then what we'll do, we will compare only x dimension, then y, then z. Again, and we will start with x, y, and z. So this is the rule basically of the KD tree, right? And each level what we do is, if we are comparing x dimension, then we will take the median of all x coordinates, or you can say that dimension points. There is one question from Sarita. Continuous regression, what's continuous regression? I guess you are referring that if the variable is continuous then it's regression. Yes, you can say that continuous random variable, you can say that it's mostly regression. If it is discrete kind of categories, then classification. But hard and fast we cannot make that argument, because it's possible that let's say you want to uh, predict like how much pizza that you will that I the sale of the pizza led in my shop, then it would be regression problem, right? But it's discrete, random variable is discrete, either one pizza, two pizza, three pizza, like that, not 1.2 or 1.3. So if the random variable is continuous or discrete, it doesn't matter, it should belongs to R basically, real value. Okay, so back to a problem. So first level is nothing but x, right? And how many data point I have in my hand? All 9 data point, right? So what I'll do, I will calculate the median of x coordinate. So median of 11, 8, 4, 1, 14, 16, 6 to 13. So the median of all these 9x would be 8, right? So now at x1 equal to 8, I will divide the data set into two parts. Either my x coordinate is greater or equal to 8, or less than 8, right? So here I have greater or equal to, just remember this, here strictly less than. So now what will happen, all my data point which has x value greater than or equal to 8 will fall into right hand side, and this will fall into left hand side. So what we are doing in geometrically, I am taking this x1. So x1 is nothing but this line from here to here, and dividing my space into two parts, less than 8, greater or equal to 8. So in my left hand side, I have only 4 points. This, and this. See, x coordinates are less than 8. 4 is less than 8. 2 is less than 8. 1 is less than 8. 6 is less than 8. Now their next parameter, or you can say the next I need to compare is nothing but my y. So at this level, I need to compare my y coordinate. So these 4 points, 2, 3, 9 and 11, I need to calculate the median of y coordinates, not x. So I need to calculate the y coordinate, a median of y coordinate. So median of 2, 3, 9 and 11 would be 3 plus 9, 12 divided by 2, 6. Alright, so median is 6. Again, I will divide whatever the data point I have, then I will take the median of x. Right, then first x, then y, then x, then y, like this. Correct. So that's how you create this KD tree. And let's take one example, a simple example. We won't be seeing this circle and anything. So let's say I have query point 13 and 5. What would be the category? So what I'll do, first I will find out like in which section the query point is. So 13 and 5. So 13, let me write it here. So 13 and 5. So x is nothing but 13 and y is nothing but 5. Right, so is x greater than 8? Yes, so I will come here. Now I need to compare y. So y is a 5, here it is 8, so 5 is less than 8, so come here. Right, now I need to compare x. So 12.5, so 13 is greater than 12.5, so come here. So I found out the neighbor e. So the class of this would be as same as the class of e. Right, so that's the idea behind KD tree, that we are dividing our whole space into parts, and we are searching in the in that part only. We are not concerned like about rest of the data points. Right, and this circle thing, just leave it for now. If you have like doubt, just watch video number 5 maybe in the old playlist, that we cover this, like what is the meaning of this circle and how exactly we are solving this problem. Right, this query point is near to a, not to e. Right, so how to find out the neighbor from, let's say, behind the border. Right, so there is one methodology, but it is not very important. So and also it's about to 11. So any doubt like in KD tree, we will have one more example for from midsem also, not from midsem, I guess mock 2. Right,
So
so yes.
yeah, basically you just draw a circle from the point you found out, and you will check whether there are any other points intersecting with it. Then
Huh.
so your calculation might be wrong, and you will take other points into consideration.
Correct,
Right?
correct. Correct. First, we take the radius as query to E, then we'll draw the circle, and we can calculate the distance between all this decision surface, right? So that's nothing but drawing the circle. We are not going to draw a circle. First, what we'll do, we will calculate the distance between this and this, the radius. Then we will see like how many points are, or you can say boundary, are within the circle. That's why we will find out we have this boundary y2. Right, this y2 we are intersecting. Then we will check like in this tray. So then you will find out that a is like near to query point basically. But that won't be the case like in our exam. And if you like still having doubt, we discussed this in last session like in very detail. Any questions guys in KD tree? We'll have one more question, very easy one.
How we constructed it, if you can quickly cover it in again.
Sure. So we have just two dimension, right? So first level it would be x, second level y, then again x, then y. Right? Just write couple of those and then start constructing. So at level one we need to compare x coordinates, right? X coordinates. So what I'll do, I will take the median of x coordinate. That's at level one. I have all 9 points. So what is the median of all this thing? 8. So at level 2, I will divide my data set in two parts, greater or equal to 8 and less than 8. So if I talk about the less than part, so how many points are less than 8? So this point, this point, this point, and this point. Now I need to calculate for y, right? So let's take the median of 11, 2, 3 and 9. So median of this would be 6. Then again I divide by using 6. Greater than or 6, greater or equal to 6 or less than 6, right? So again I will have the part like 3 point on this side, and sorry, 2 point on this side and 2 point on this side, like that. Correct. And we do this like till we classify all the points. And there is one more parameter in KD tree, that how much points you want to have on the on the leaf, right? If it was 2, then I will stop here basically, because after this I have just 2 points D and G. But currently I am saying like on my leaf node I want 1 point each. That's why we are classifying on X parameter, or you can say X coordinate, right? So there is one more parameter like how many leaf node you want to have. But that's very much useful in some data structure. This tree, you can say tree is a kind of a data structure used in some algorithm. Okay.
Mayur, if there are three dimensions, then how it will work? Like x,
XYZ,
first,
simple XYZ.
first will break to x, then y, then z,
Huh.
and then again x, y, z like this.
Correct. First dimension, second dimension, third dimension, like that. Then again
And
one,
then
two, three.
again to the first.
Yes, and in real world it doesn't matter, right? Because we have features, feature one, feature two, feature three, but same order you need to follow. That's the rule. Okay. I have given this very also, you can say detailed note. I have written like how to you can say construct a KD tree and how to search in a KD tree, right? And two more video. Let's take one more. You can say this thing, or you can say second last topic of a day. Not of a day of this PDF. Sorry, locality sensitive hashing (LSH). Right. So the idea behind LSH is given the data point, we generate n number of random hyperplane that will divide my space into you can say number of regions, right? If you take the example of today, if you take this, let's say two hyperplane, three hyperplane, four hyperplane, you can take like n number of hyperplanes, right? And what it will do, it will divide my space into some regions, and for each region I can give some code, right? And how this code is given is, let's take I have this hyperplane x plus 2y equal to 0. So this hyperplane is nothing but 1 2, right? W1 is equal to 1, W2 equal to 2, passing through origin. That's why W0 or B is 0. So given this hyperplane, it will divide my space into two half, positive half and negative half, right? So all the data point on this side of hyperplane 1 is in positive half. All the data point on this side of hyperplane is on negative half. Similarly for this hyperplane, this half is nothing but my positive half, and this half is nothing but my negative half. Now, using this, you can say, using this method, right? By coding the region, this region would be 1 1. Why? Because it is on positive half of hyperplane 1. So this first letter is saying like on which half this point is, or you can say this region is. So this region is representing plus plus of plus plus, right? Because see, all of this side would be plus for hyperplane 1, and this would be nothing but negative for hyperplane 1. Negative, negative. If I talk about hyperplane 2, all of this would be positive, positive, positive. And on this side, see in this blue side would be negative. So negative, negative. So that's why I am saying plus equal to 1 and minus equal to 0. You can say 1 and minus 1 also. There is no problem. You can encode it as the way you like. Right? So this whole region is nothing but 1 1. This whole region is nothing but 1 0. This whole region is 0 0. This whole region is 0 1. So using two hyperplane, what I am doing is dividing my whole you can say space into number of regions, or you can say buckets. Now I will use dictionary data structure and store all these neighbors, or you can say all the points in the region, right? In the region, I might have like some bunch of red points, green points. It doesn't matter. But given data points, so like what is the you can say advantage of using LSH, right? So given a query point, what I'll do, given a query point, let's say I have query point here, I will first find out in which region it is, right? So given query point, we can determine, right, if it is on hyperplane positive half or negative half, or hyperplane one is positive or negative. Right now we know, right? Just put the value or take the dot product between point in hyperplane, and you will know if it is plus on the positive half, if it's negative on the negative half. Right, so now I know like what region it is. So given the region, I will find using the dictionary, I will find out all the data points in the region. So literally I am using just 25%, roughly 25% of a point. I don't care about the rest of the points, right? So we are limiting our search. Basically in brute force, I need to calculate the distance, or that cosine similarity, or any other thing for all the points, right? Which is not very good idea, right? Or time consuming also. So using LSH, I am just bucketizing all the data points, and for given query point, I will find out the region first, and then I can apply like Euclidean distance, Manhattan distance, cosine similarity to find out the nearest neighbor. Given query point, I just talk about only these points, right? So that's the idea behind LSH. Just find out, just take the dot product of the point with the hyperplane, right? Whatever the answer you get, if it's positive, it's in positive half, so just say plus or 1. Just take the dot product of this point into hyperplane 2. If it is positive, then write plus, or you can say 1 also. If it is negative, you can write 0 or -1, right? Any doubt, guys? We have one question, I guess, for LSH also, bucketizing the thing. Let me pull it quickly. Mock 1 maybe. Yes, this thing. We had this 8 data point they have given. Given the 8 data point, say that we use the two planes having the weight vector 1 -1 and 2 2, and performance LSH using cosine similarity. Then which of the following grouping or bucketizing is correct, right? So there were four options, and we need to do this thing, right? So surely we will see this example also, then again it would be great revision, and you can say great understanding also, right? So there's nothing but nothing fancy, just we need to take the dot product, and that's all. Okay guys, any questions like in LSH till now? Let me have yeah.
What if the point passes through the plane?
Point passes through the plane, it would be zero, no? So you can consider zero in the positive, right? You can give that condition. If the dot product is greater than or equal to zero, then it's positive half. Or less than zero, negative half. Correct? Because it doesn't
Yeah.
matter if you count zero in positive or negative, because it's basically on the plane, right? So whatever the condition you give, it would be like bucketized in that fashion. Just give me a second, guys. I just need to have some water. It just got finished. बॉटल क्या गई पानी बॉटल नहीं है हाँ दो मिल okay guys, so last one, this is like very last chances of being exam, because this is very, you can say, this thing complex thing, but let's try to understand this. So LSH for Euclidean distance, so what they are doing is
By one more part, I think you missed a case where I think you'll use multiple planes, right? Like
uh,
there is one disadvantage in this method, and there is another method where
we take the
N hash
iterative
tables,
method, right?
L hash tables. So you take multiple hash tables,
multiple hash tables, and you will take the majority.
majority. Yeah.
Hmm.
Okay. Is it covered below, or I think
No,
you?
no, it's not covered here. So
Sure.
let me give a brief about it. So it's possible, right, guys? Say after doing this hyperplane, this thing, if something is, let's say, very near to this boundary, right? This query point is very near to boundary. Yet it is like it is very chance like it is red. It's of red category, but it will be classified as green. Why? Because of this hyperplane one, we are dividing this point into in this half, right? So we won't consider this f1 point and z point. We will consider p and I. So the nearest neighbor would be p and I. So it would be classified as green, right? But the most nearest neighbors are nothing but the red one. So how to overcome this, right? So let's assume that let's say my hyperplane was something like this, then it would be like on the right hand side, then it would be classified as red, right? So what they are doing is, and say this is not you can say the deterministic approach LSH, it's the randomized algorithm, because randomly we are choosing hyperplane, right? So what they the hack that they are using is, given the data set on let's say 2D surface, what they do is, they, let's say we I want to have two hyperplanes, right? Two random hyperplanes. So first they will take two random hyperplanes, again they will take two random hyperplanes like this, again they will take two random hyperplanes. It can look anything like this, right? Two random hyperplanes. After taking taking this n number of, you can say, hyperplanes. See, if I take hyperplane 1 and hyperplane 2, something like this, it will construct some hash table, or you can say some dictionary of r11 may consist of this point, like a to b or a to d. But in this point, it will be classified like in let's say r10 bucket, it would be there. So what I'll do, after taking all this n hash table, and this all n hash table has the different number of points, right, in each bucket. So then we can take the average also, or while calculating the neighbors, constructing the neighbor, I will consider all the neighbors from the all hash tables. So I will consider this neighbor also, this neighbor also, this neighbor also, this neighbor also, this one also, right? Then I will make the good guess that it's red, right? So this is the one hack that they are using, because the problem here in this random approach is, due to, if you take just two hyperplanes, then it's like very very high chance that we make a mistake, right? If it is this or age case, basically if the point is very near to age, or basically on the hyperplane also. So if you take like n number of hyperplane, then this issue would be resolved basically, correct? uh, See, problem and solution. See, if very near to hyperplane, then some class point on the adjacent region, we may classify the point, right? So to solve this problem, we take the multiple sets of hyperplane, and we then create the hash table. That's all the nearest neighbor in the age case. Age are also you can say included, correct? The last topic for it's nothing but the Euclidean distance. So what we are doing is, we are taking the random hyperplane, but this random hyperplane is divided into some parts, one, two, three, four, five. Also this hyperplane is also divided into one, two, let's say three, four, five, correct? So I am dividing my hyperplane into some regions, or you can say segments. Say this is segment 1 from here to here, this is segment 2 from here to here, and segment 3 from here to here, right? Again I have this segment 2 1, because this is hyperplane 2, here to here, here to here. So I have these three segments, right? Now what I'll do, I will take some point, let's say I have some point here, some point here, some point here. I will take this kind of a thing. What is that called? Projection of a point, right? Projection of a point. Projection of a point, of this point. Now how to give label to this point? So it is on region 1, and here it is on region 3, so it is nothing but 1 3. It is on region 2 2, so it is 2 2. If it is on region, let's say 1 and 3, sorry, 3 and 1, so it is 3 1. That's how we are classifying the point. Just take the projection on a hyperplane, and whatever the region, or you can say segment, they are falling in, just give the number, right? So if you take this point L, it is on segment 1 on hyperplane 1, so first coordinate is nothing but 1 1. And for hyperplane 2, it is falling on segment 3, so it's nothing but 3 1 3. The bucket of L would be 1 3. So it is not easy to calculate on by on pen and paper. We simply need some coding or any other tool, so it is like very very less chance to be asked in the exam. But it's good to understand, right, how we are doing using the Euclidean distance. Correct. So this is 1, this is 2, because it is falling on the segment 1 on hyperplane 1, segment 2 on hyperplane 2, like this. Correct. And after creating all the bucket, we know like the all the nearest neighbors. So given the query point, just go to that bucket and perform that cosine similarity or anything. So using this LSH and this Euclidean distance KD tree, we are just limiting our, you can say, search area, because it's not you can say smart, or you can say very good way to calculate distance of all this data point, right? Just to find out the nearest neighbor using LSH, or let's say Euclidean distance, that LSH for Euclidean, or KD tree also, some parts, and then search like in this area only. Right? We are limiting our search for from the whole data set. So that's the whole idea basically. Any questions, guys, till now? Okay, one topic we
Well, in
have.
the last one, this LSS for Euclidean distance, what where is the query point?
See, let's say I have one query point, right? Let's say I have some query point here. See,
Okay.
if points are very very near, no, let's say I have some query point here, let's say, right? So it would fall on segment one. So the point would be one, and it will, let's say, fall somewhere here, 90 degree. So 1 2. So then I will go to dictionary and find out like which is very similar. So I will find out I is very similar. So if k equal to 1, I will say the category of this query point is green, right? You like
Got it,
the,
got it. Yeah, got
yeah,
it.
the
Yeah.
idea is simple, right? If the point is very near to q, then again it will fall on the same segments, right? So in training data set, we are noting down all these segments. So all the points near to I will fall into same segments. Correct. So basically, we
Um,
are in advance. We know like which are the nearest neighbor.
Mayu, did you tell how we need to put the segments?
I guess it's random, right? If I'm not wrong, and there is one parameter, the length of a segment, but not random, but it's sequential, right? Segment one, then segment two. This length of a segment is a parameter. I guess in some library I saw that length of a parameter you need to provide. Right? If you give the very small length, then you will have so much of segments, right, on the hyperplane. So number of hyperplane and length of segment is the hyperparameter, you can say. Uh, it is not covered like in much depth also in our content also, this Euclidean distance, because see, this is very complex. No, this is very intuitive and very cool. This LSH for cosine similarity. Last two topic, very simple one, time-based splitting and probabilistic class level. So time-based splitting is useful if you have like some date feature. If in your data you don't have date, or you can say time basically, and your data set doesn't depend on time interval, then this doesn't make sense. You cannot perform, right? But let's say you have some kind of a data which depends on time, right? Time axis, right? So then you can use the time based splitting. Why? Because like your data like depends on time. As the time increases, or like on the interval of time it changes, like there is some change in data, and you want to predict that, right? You don't want to mix all the things. So the example that was given in our content was like, as the time changes, the product description might change, the category of products might change. You will add more products in the same category, or you will remove some products from the category, right? So basically, we are doing some changes over the time, right? So in that case, what they are saying is, let's say you have 40 years of data, then definitely just take like 20 years of data for training, 10 years for cross validation, and again 10 years for testing. So what you are doing is, you are like doing all the training and cross validation stuff on 9080 to 2010 only, right? So you don't know the data of 2011 to 2020. You have it in your hand, we are in 2021, but your machine learning model don't know it, right? Doesn't know it, the data of 2011 to 2020. So what we are doing is, we are mimicking the real world scenario. In real world, what will happen after doing like all this machine learning stuff and everything on this day, right? August 2021. I will say like, this is my machine learning model. Just deploy on, let's say, AWS or anything, then it will start working for, let's say, next 5 years. So what it will do, it will face the future data. So what we are training is, in our training phase, what we are doing in time based splitting is, we are just providing the data set of just first 30 year, 1980 to 2010. And after 2010, what I'm doing is, from 2011 to 2020, I'm using as the test data, right? So we are just mimicking the scenario, real world scenario, that they are training on the past data, and pasting on the future data, right? So this is the advantage of time based splitting. If you like take the random splitting, then it's possible that you have some data from 1980, 2010, 2010, or 2011, 2015. So it would be simply mess up, right? So your model knows like everything in advance. So this is some hack if you have date column or some time dependent features. What is this probabilistic class label? So see, this is nothing but the simple answer to KNN, majority voting. Let's say you have at same distance, you have this 9 points, k equal to 9, and you have 4 points from class A and 5 points from class B. So everything is at same distance, right? 3 and 4. Now, what will you say for this point? Is it of class A or class B? So if you take the majority voting, you will say it's class B. But see, like it's neck to neck, just 4 point to class A and 5 point to class B. Just the difference is just one. So how can you say that like 100% this is class B? No, you cannot say that. So what I'll do, I will calculate the probability. So how will I calculate probability? What's the probability of class B? We are not using Bayes theorem here, guys. So 5 by 9, 55.56%. That it's 55% chance that it's class B and 44% chance it's class A. So this is good idea, right? Rather than saying no, this is class B 100%. No. So this is nothing but the probabilistic class label, or you can say class label technique in the KNN. Correct? Any doubt, guys? Now, like we will see some action and fun basically, and that's nothing but that confusion matrix. Okay, 11:20. I am sure like we won't be able to cover that LRD, LOF, and everything, but let's see. Any doubt, guys, in this KD tree LSH? It would be very clear when we solve one more question. Uh, KNN for regression, this overfitting, underfitting in KNN. If you doubt, I don't know like how to explain.
Uh,
Yes.
Mayur, do we have any assumptions in KNN like we have in naive phase? We have an assumption that features are independent in naive phase.
Uh huh.
So do we have any these kind of assumptions being made in KNN?
One I can think of is like you have like good separation of different labels or different class labels. I guess that's the only assumption I guess we have in KNN, right? Because if it is mixed, then you can this KNN will not work. That's simple noisy data if you have.
You
So
mean to say linearly separable
the
kind of?
clusters, basically clusters of not linearly. Why linearly? In KNN, it's possible that if you don't have linearly separable data, it's fine. Correct, because we just care about the nearest neighbor, k nearest neighbor, right? So basically the one class label should not be mixed with second class label, right?
Too
So
much
the
of
cluster,
jumbled data.
not jumbled data, yes. The clusters of this class label should be separable, basically, not not necessary linearly. Okay, guys. So this is like I plan to cover up to four this thing, but I'm not sure if we would be able to, because this will take some time. There's LOF, LRD, and everything, and before that, this confusion matrix thing. So let's see how we proceed. Uh, what is this? Not this one. This one. Okay, so confusion matrix, that everyone has the confusion. I am like sorry if I'm like using the this inverse. You can say this thing, because in our lecture video, sir is written predicted value here and actual value here, but I am following the sklearn standard. So in sklearn library, actual value it is in left side and predicted on the top side, right? So what confusion matrix is saying, let's say I have some actual values, total observation is n, and I'm following some different you can say this thing also, different notations also. So what those notations are, ap is nothing but actual positive. So how many actual positives you have? An actual negative, ground truth, basically that y is 1, y is 0. What you are predicting, I don't care, this is truth. PP is nothing but predicted positive, and PN is nothing but predicted negative. So what you are predicting, right? How many points you are predicting is positive, how many points you are predicted is negative. So PP and PN, right? So let's say I have n equal to 200, 100 are positive, 100 are negative, and I am saying 110 are positive and 90 are negative. So see, the 110 out of these 110 positive points that I have predicted, P predicted positive, 90 are true positive, right? 90 are true positive. What is true positive? It was positive and I'm saying positive, so it's true positive. True means okay, positive, okay, right, correct. And 20 are false positive. That means it's negative, basically, but I'm saying it's positive. So false positive. False means no positive. That means it's actually negative. Right? False negative. That means false negative, no negative. So actually it's positive. Right? So false negative is nothing but type 2 error. That's the data set was point P, or you can say positive 1, and I'm saying it's 0, negative. So it's nothing but false negative and true negative. So TPR, or true positive rate, is also called as sensitivity, or also called as recall. Right? And you will be surprised, there was one MSQ where they says TPR equal to recall. And it was right. True positive rate equal to recall. Yes. Right. So TPR, true positive rate, or recall. So recall, like, and sensitivity. Sensitivity is like how sensitive your model is, right? Because mostly we care about this positive result. That means we are able to find out the positive category, that if it will happen or not. So true positive divided by actual positive. So out of actual positive, how many you are able to get? So it's nothing but the sensitivity, how sensitive your model is, right? So TP divided by AP. And we have one more something called precision, or PPP, predictive positive value, or something like that. So precision is nothing but how precise your model is. So if I'm saying 110 are positive, so actually how much are true positive? So predicted positive, true positive divided by predicted positive. So out of 110, you can say positive points, predicted positive point. How many are actually true, right? So this precision will be useful if my model is dumb. If it is saying all 200 points are positive, let's like say positive and chill, right? In that case sensitivity would be So all 100 points I will get, right? And this predicted would be 200, all this thing. So my sensitivity would be 1. So you'll be cool, right? Recall is 1, all 100 points I am able to get it. But this precision would be 0.5, 50%. That it's not precise. It is saying all positive, all the points is positive, right? So that's the idea behind precision and recall. F1 score is defined something like this: 2pr divided by p plus r. 2pr, p is precision, r is recall, right? FNR, FPR, FTNR, I have just given the formula, just go it like once. And accuracy is nothing but how many correct points you have: true positive plus true negative. So this principal diagonal they are saying. So the principal diagonal should be maximum, right? Because on the principal diagonal I have all the true thing, or you can say success or correctly classified point. Positive is classified positive, negative is classified negative, right? So in this principal diagonal I should have the maximum value. So this is just I have two category, that's why it's 2 by 2. If I have six category it would be 6 by 6, right? So this principal diagonal should be maximized. And the accuracy is nothing but all my true, you can say, classification, correct classification, that's nothing but true positive plus true negative divided by out of all the numbers, divided by n. So n, if you think about, is nothing but TP plus nfen plus FP plus 2TN. So if you sum everything, it would be 200, no? So it's nothing but n. So it's nothing but the accuracy, right? When to use what? We are not going to cover that. ROC AUC curve. So ROC is nothing but the receiver operating characteristics, and it is it is very useful, and it has some limitation also. That ROC, it's calculated using the different threshold, right? So let's say I have some, you can say, data, and I want to predict the category if it is not obese or obese, right? And given the weight, the category is given here, right? So this is nothing but the ground truth, and this is the probability value that my model is saying. Let's say I'm using SVM or logistic regression, it's saying my probability of obese, right? Now how to know like where to put the threshold? What is the good threshold? If I put the threshold here 0.05, then everything would be classified as obese, right? Because everything is greater than 0.05. So if I put the threshold at 0.13 somewhere here, then this would be classified as not obese because zero point 0.1 is less than 0.13. But 0.152, everything is like greater than 0.13. So everything would be classified as obese. If I put zero point 0.2, then some story, then some story, then some story. So which is very good. How to determine that, right? So what I'll do, for each point, each threshold, I will calculate true positive rate and false positive rate. At how many true positive I am getting and how many false positive I am getting. Right, so true positive should be highest and false positive should be lowest. So if TPR equal to 1 and FPR equal to 0, balle balle, it's good. False positive I am not getting anyone, and true positive I am getting everything. Every positive value I am able to find out truly. Right, so it's TPR versus FPR graph. So this should be the highest and this should be the lowest. So for each threshold, I will calculate this thing TPR and FPR. If it is 1 1, I will put here 1 1, then 1 0.75 somewhere here, 1.5 here. So it is good, right? My TPR is 1 and my FPR is decreasing. Cool. But as soon as I go to T4, my TPR is 0.75 and my FPR is 0.25. Okay, that's also cool. 75% is cool. Again, I increase the threshold, then I go to T5. Okay, good, right? Because still my TPR is 0.75 and my FPR is, you can say, decreasing one by one. So at T6, right? So T6 is the good point, right? High, like good TPR, and FPR is almost zero, basically zero, right? So this is nothing but the ROC. And if you calculate the area under this curve, it's nothing but AUC. Right, higher the AUC, good the model is. So This is just the simple 8 threshold. You will basically calculate for thousands or more than thousand thresholds also. So let's say I have some model whose AUC ROC is looking something like this. This is 50% line, right? And one more model whose ROC is looking something like this. So this model is better than this model. This blue model is better than red model, right? So higher the area, because this area under the curve is higher, correct? So if you calculate the area, this would be higher than this amount, right? This blue will have the higher area under the curve compared to this red curve, right? So you will choose this model. Let's say this is logistic regression and this is SVM. Go with SVM, correct? So this is ROC AUC. It's 11:30, guys. So I just need your feedback. Should we finish this log loss and MAD, this distribution of error, or tomorrow? Because this is pure mathematics, nothing fancy.
We can have it tomorrow. Maybe.
Okay, sure. So from log loss, we will start from tomorrow.
Sure.
And yes, definitely, I want to finish the theory first. Or guys, if you have like feeling that okay, I know this kind of a theory, we can jump onto numericals directly. Then I'm also fine. That first finish all the numericals, and if time permits, take the theory, like the common, you can say, doubt session like on the theories. Any comments on that?
Because theory also would help, right, to understand the numerical also. Yeah, Major. Correct.
Sorry.